Hello. I wanted to um, recap what we've done so far and then start with our main theorem. So far, we have discussed how the set of bounded functions, real valued functions from a closed interval AB is a complete metric space. So just to recall, CB is going to be functions that are bounded and really the complete notation would be CB, AB, comma, script R, right? So you put the domain and then the codomain. But so it's a complete metric space. That means that all Cauchy sequences converge. The metric is given by the norm, the suit norm, okay? So the distance between, so if you have F and G, the distance between F and G is defined as the supremum over all x in your domain of the absolute value or the distance between f of x and g of x. Okay, so it's a complete metric space. And since we have the set of Riemann integrable functions and continuous functions as subsets, we proved that C naught and script R are closed. I already see a little typo here. This should be C naught and the 0 should be a superscript. So C naught is closed in the set of bounded functions and script R is closed. So this gives us the two main results. Number one, the uniform limit of continuous functions is continuous. And number two, the uniform limit of Riemann integrable functions is Riemann integrable. Plus, we know that the limit of the integrals is the integral of the limit. Okay? And now our goal is to learn in what way, not how, in what way uniform convergence preserves derivatives. So we've already seen that it preserves continuity, it preserves integrability, right? It also preserves uniform continuity. So now we're going to look at uniform continuity and derivatives. Okay, so here's the official theorem. The theorem says that the uniform limit of a sequence of differentiable functions is differentiable, provided that the sequence of derivatives also converges uniformly. So just to break this down, what does this mean? Remember, for our notation, we had that, so if we write Fn converges uniformly to F, then this F is the uniform limit of these functions right here, these limiting functions. So here, in our statement of our theorem here, we're saying the uniform limit of functions that are differentiable will be differentiable. So that limit will be differentiable, assuming that the sequence of derivatives also converges uniformly. So for our hypothesis, we say suppose we've got a sequence of differentiable functions and they are uniformly continuous. So the derivatives are uniformly continuous and the original functions are uniformly continuous. The claim is that that limit function f is actually differentiable and its derivative is what we want. Its derivative is the uniform limit of the derivatives. Okay. So to prove this, we actually split it up into two cases. Case one is a very specific case, and case two is a more general case. So for case one, we're going to assume that all of our derivatives are in fact continuous. And now doing this, we're going to prove that that limit function, the uniform limit, is differentiable, right? And we're going to do it using the fundamental theorem of calculus and a lemma. For case 2, where we make no assumptions about the continuity of our derivatives, we'll essentially use helper functions and prove that those helper functions are uniformly convergent and they converge to a continuous function, and therefore we'll get our desired result, which is that our uniform limit is differentiable and the derivative is the derivative of the is the limit of the derivatives. Okay, so let's start off with case 1. Remember we said we needed a lemma. Here is the lemma we need. Okay, the lemma is this. Now keep in mind that we already know that fn's converging uniformly to f, and the fn's belong in the script R for all n implies that f is Riemann integrable. So this is a little twist, and this one is talking about the indefinite integrals converging uniformly. So assume that we have a sequence of Riemann integrable functions, we'll call them fn, and they are uniformly convergent to some function f. Then we're saying that the indefinite integrals converge uniformly to exactly what we want them to converge to. Okay, so I'm introducing this notation here, fn and big F of x. The goal is that for each x, fn converges. So for each x, we've defined fn and f, big Fn and big F. And the claim is that big Fn converges uniformly to big F. Okay. Now remember we had 3 different characterizations of uniform convergence. One was using epsilons, another was using the epsilon tube for the graph, and then this last one, which is the characterization we'll use here, relies on showing that the distance between the fn's and the f's goes to 0. This is the suit norm. Okay. Now, let's see here. To better estimate, so this is our goal. Our goal is to show that the suit norm of the fn minus f's approaches 0 as n goes to infinity. So fix x in our domain, and then what is fn of x minus f of x, or big Fn of x minus f of x? What is the difference of these indefinite integrals? We just took the absolute value, and now we'll be able to combine. Let me see here. Here we go. We should be able to write equals, and then we'll have the integral from a to x of simply fn of t minus f of t dt. Okay, since we're integrating over the same domain, we have this property. And now we can say that this is less than or equal to, this is by a triangle inequality, fn of t minus f of t dt, absolute value, the distance between fn and f. Next thing we're going to do is we're going to note that this is less than or equal to x minus a times the suit norm of fn minus f. Now, how do we get that? Well, just remember this suit norm. This is the sup of fn, t minus f of t. T is in between a and b, right? This integrand is always going to be majorized by, therefore, the suit norm over all t's, right? So not just t's in between a and x, it'll be less than or equal to the suit norm over the entire domain. And now all we have to do, remember what's our goal? Our goal is we want to show that the suit norm goes to 0 So all we have to do is say that we have a uniform bound, a global bound, if we say that this is now going to be less than b minus a times the sup norm. So what I want to point out is that on the left-hand side, we have an expression which depends on x. But here, we have found an upper bound. This is independent of x, right? So our conclusion is that the sup norm, the sup of the fn of x minus f of x of these indefinite integrals has to be less than or equal to b minus a times the sup norm of the integrands, right? So actually, this is what we have. And now the last thing we need to do is take the limit as epsilon goes to, not epsilon, sorry, as n goes to infinity. Right, so really we're squeezing. So this is going to go to 0. This is already 0. Now, why does this expression over here tend to 0? That's the question. And the answer is, in our assumption, we assume, in our hypothesis, we assume that the fn's converge uniformly. So another way to write this is the sup norm goes to 0 as n goes to infinity. Okay. All right, so we are done with our lemma, and we can confidently move back to case 1. Remember, our entire goal is to figure out or to prove the theorem that tells us how uniform convergence preserves differentiation. Okay, and we said we're going to split it up into 2 cases. Case 1 is assume that your derivatives are actually continuous. Okay, if your derivatives are continuous, then we've got the following things that are true. First, for each x, by the fundamental theorem of calculus, we can write fn of x is equal to f sub n of a plus the integral plus the indefinite integral of f sub n. Okay, that's just by the fundamental theorem of calculus because our f's are differentiable. Okay, now part 2 is we can say that these indefinite integrals converge uniformly. On AB. So what am I going to do? I'm essentially going to say that this is converging uniformly to my indefinite integral here. Let n go to infinity, and fn of a is going to approach f of a. Why? Because in our hypothesis, we're assuming that the fn's converge uniformly to f. So at any single point, the fn is going to converge to f as well. Okay, now I put it all together, and since fn, so basically I'm using this right here, this equation, to conclude that the fn's are going to go uniformly to f of a plus the integral from a to b of g of t dt. Okay. Now, remember in our hypothesis, Fn goes uniformly to some function f, right, by hypothesis. So if Fn is going uniformly to f of a plus this indefinite integral, and Fn is converging uniformly to f, by the uniqueness of limits, it must be that f of x is equal to f of a, right, plus the integral from a to x of g. Now, by the fundamental theorem of calculus, it has to be that this g right here is, g of x is f prime of x. And this is by the fundamental theorem of calculus, right? It says that indefinite integral is differentiable and its derivative is f. Okay, so case one, pretty straightforward because we have the strength of the fundamental theorem of calculus. Let's look at case two. So suppose we don't know we do not know that all of our derivatives are continuous. What do? Well, in this case, we're going to form the following helper functions. So you fix x and AB, and then you're going to form this sequence phi sub n of functions from AB to R, and phi sub n takes t and sends it to either fn prime of x. So this right here is the slope of the tangent line at x. And if t is not equal to x, then we are sent to the slope of the secant line through t fn of t and x fn of x. Okay? Now, question, why is each phi sub n continuous? Answer, each phi sub n is going to be continuous. Say fix t. Case one, t is equal to x, because remember x is fixed. So if t is equal to x, then the limit as t approaches x, phi sub n of t is going to be equal to limit t approaches x of fn t minus fn x over t minus x, and that is precisely fn prime of x, since each fn is differentiable. Okay. So we now have the phi sub n's, they're continuous. Second question, what is the pointwise limit of our sequence? Answer, well, oh wait, did I finish up over here? So I said if t is equal to x, then we've got this. What about if t is not equal to x? If t is not equal to x, we're trying to show that phi sub n is still continuous at t. Then near t, or say we call that t naught. So fix t naught. If t naught is equal to x, then okay, let's see here. Since each fn is differential. Now if t naught is not equal to x, then near t naught, phi sub n of t is equal to, and I'm just going back to this formula right here. Okay, so I have f sub n of t minus f sub n of x divided by t minus x. So this is a function of t. and it is going to be continuous because this is a constant, this is a constant, and wherever it is, so let's put here t not equal to x is what we're saying. Then what we get, we will get this continuous function in t, right? Continuous in t. So the quotient of continuous functions is again continuous, and we don't have to worry about dividing by 0 because we are in a situation where our t naught is not equal to x. Okay, now let's get back over here. What is the pointwise limit of phi sub n? Well, what do we need to do? We just need to say fix t, say fix t naught in AB. We need to compute the limit as n goes to infinity of phi sub n of t naught. Now, here's our phi sub n. If we fix t, then what is the limit? It's n. Well, let's see here. So as n goes to infinity, the f sub n of t should approach f of t. Why? Because the f sub n's are converging uniformly to f. So I want to write that down. Limit n goes to infinity, and this is fn of t minus fn of x over t minus x. Now here, notice that the t and the x are fixed. That's just going to be equal to f of t minus f of x over t minus x, okay? Now what about, so we'll get this. This is if t is not equal to x. If t is equal to x, then the limit n goes to infinity, phi sub n of t is equal to the limit n goes to infinity. Now, if t is equal to x, then we're just supposed to use f prime of x, or fn prime of x. And the fn prime of x, the fn's are supposed to converge to g, so this should be just g of x. So let's say phi sub n goes pointwise to phi, where phi is defined as, and we'll have two options, g of x if t is equal to x, and if not, we'll have f of t minus f of x divided by t minus x if t is not equal to x. Okay, now we actually want to show that phi sub n converges uniformly to phi. Okay, so how are we going to do it? Now, why do we want to show this? Actually, let's go into why we want to show this. So we're asking kind of, who cares? Well, then, since the phi sub n's are continuous, if phi is the uniform limit, this will imply that phi is continuous. And if phi is continuous, remember, according to our definition, that means that the limit as t approaches x of phi of t is equal to phi of x. And plugging everything in, that would be g of x. And this would be the limit as t approaches x of f of t minus f of x over t minus x. And that is precisely, so since that limit will exist, we will get f prime of x equals g of x, which is what we want. Okay. So now we just need to show that the phi sub n's converge uniformly to phi. First thing we're going to do is we're going to say fix x and t. By the mean value theorem, we'll be able to show that there's a theta such that theta is in between x and t, and this part right here is true. Now, we are applying the mean value theorem to fm minus fn. So this is a brand new function. It's differentiable. In the interior, it is continuous on the entire domain of AB. Okay. Now notice that this left-hand side is actually equal to phi sub, let's see here, I think phi sub m So looking at this, we get phi mt minus phi mx, okay, and then minus fnt, and then minus fnx, okay, is what we're working with, and all this is over t minus x. And this is now the same thing as phi sub m minus phi sub n of t. Okay? And so we're going to say that since our sequence of derivatives is uniformly convergent, it is also Cauchy. So we've got a bound, right? So phi sub m minus phi sub n, that norm is less than or equal to fm prime minus fn prime, the norm of the difference of those two functions. So if this goes to 0, since it is uniformly convergent, then this also goes to 0. Okay? And so when I say this goes to 0, as m and n get really big, that's another way of formulating Cauchiness. Okay? So just to cap it off, as we were saying before, our phi sub n is uniformly convergent. And since each phi sub n is continuous, the phi sub n's will converge uniformly to phi, and phi is in C naught, so that f prime of x is equal to g of x. Okay. And that's it for now.